Last time we finished off chapter 8. Let me start chapter 9, functions. So, section 9.1, introduction to functions. So first let me give you the idea of a dependency statement. And so a dependency statement is some sort of statement involving a of quantity. We'll call it a dependent variable. So the dependent variable and this dependent variable is completely determined by some sort of relationship. And so it's completely determined by the independent variable. And so we want to determine what the relationship is between this independent variable and this dependent variable. And so let me do on page 353, let me do problem number 6, the surface area S of a cube in terms of the lengths of each of its edges, which we'll call x. And so let me write a dependency statement involving these. And so in exercises 1 through 13, write an expression that describes one of the variable in terms of the other. Okay, so let me do that. So let me draw a picture. So in this case, let me draw a cube. So this is some sort of cube, and each of its sides will have length x. Well, the area of a rectangle is length times width. And so if I look here at the top, well, the area of the top here is just going to be length times width. It's just some sort of rectangle. Matter of fact, it's a square. And this will have length x, and this will have length x. So x times x. So this is x squared. The area of the bottom again, if I look at the bottom, it's just some sort of rectangle. Matter of fact, it's a square. The length of this side is x, the length of this side is x. So it's x squared. And so the area of a side, so if I look at one of these sides here, let's say the front, so if I look at the area of the front here, it's just length times width. Again, just x times x, x squared. The length of the back, the area of the back, again, the back here is just a rectangle, so it's x times x, it's a square, x squared. The area of, well, let's say the right side, again, this is a rectangle, it's a square, each side of which is length x. And lastly, the area of the left side, length times width. Again, it's a square, and so the area of this is just x squared. And so there are a total of 6 sides. Each of area x squared. And so each of these have an area of x squared. So there's 2, 4, 6 of them. So therefore, the surface area of, of this cube is just 6x squared. And we write the fact that this this variable, s, the dependent variable, depends on this independent variable x. And so we write this in, well, let me do it 2 ways. Let's just write it as the surface area is equal to 6x squared. So this is my independent variable. And this is my dependent variable. And so we can write this in functional notation. The fact that my dependent variable depends on my independent variable by the relationship of 6x squared. And so the surface area is just 6x squared. Let me do problem number 10. The length L of a part of the number line segment between 2 and 5 in terms of n, the number of equal parts into which it is divided. Okay, so if I look here, I have here the number line from 2 to 5. And so this distance here between 2 and 5 is 3. So if I divided it into I don't know, let's say two equal segments, then two equal segments. Then each of these would have a length of 3/2. If you added 3/2 plus 3/2, you'd get 3. If you divided it into n of these, let's say a whole bunch of these, and so n equal segments, then each of these have to have a length of 3 over n. Because if you add up all these n of them, then 3 over n plus 3 over n plus 3 over n dot 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 plus 3 over n, if you add up n of them, then you just have a total length of 3, just like what we had up here. And so that says that the length is just going to equal 3 over n. And so the length of each of these line segments will just be some function of how many equal line segments you've partitioned the interval 2, 5 into, n. And each of these will have a length of 3, in each of these little line segments will have a length of 3 over n. Any questions about that? Okay, so let's recall from grade school the function machine. So function machine. And so we have some machine here. And well, we will input something, and then the function machine will do something to it, and then it will give us an output. We can think of this as, I don't know, a vending machine. So you put in some money, you then uh, make some sort of selection. So it, and then you get some output. Okay. And so this input is your independent variable. Usually we'll denote it by X. Your output is your dependent variable. It will usually denote it by Y. And this is a unique output, meaning that if you input your selection, say that your input is, so this is a vending machine, and you have an input, and your input is that you've selected what you want, then the output has to be unique. So when you input your selection to a vending machine, you don't want all of a sudden you to get, coal when you wanted a candy bar. You want that when you select your selection for this function machine, that you know what you're going to get out. So that once you've made your selection, your output will be unique. And so no matter when you put in your uh, input, if your input is the same, then your output will always be the same. And so that's the idea of some sort of function machine. And so given an input, you will have a unique output. So let's do on page 354, problem number 16. G of x equals 3 minus 5x plus x cubed. So in these, what we want to do is we want to give names to these differing types of functions. And so in exercises 14 through 26, classify the function as a power, polynomial, rational, absolute value, radical, or piecewise defined function. Okay, and so I want to classify these. Now, in this case, since we have the sum of a whole bunch of terms, and each of these terms have a variable to some sort of whole number power, then I will call this a polynomial function. Now, of course, it could be called other things. It could be called a piecewise defined function where there's only one piece. It could be called a rational function where you're just the denominator is one. Things of that sort. But it could be called a radical function where it's just the your exponent is a power of one. But we would normally classify this as a polynomial function. So even though it may have quote unquote technically other things that it satisfies, you want to sort of give the standard uh, sort of terminology. So if I have some function of the form a to the n, x to the n, a to the n minus 1, x to the n minus 1, all the way down to x, let's say 0, then this is called a with a0, a1, up to an real numbers, and n a whole number, then p of x is called a polynomial function. We actually have a notation for it, so maybe I should say that. I say that this is a polynomial of, well, you could say degree n, and the variable is x, and the coefficients are real. And similarly, let's say that, so whatever the particular field I have this polynomial on, I'll denote it by this thing on the outside. So let's say that the coefficients were rational. Then I would put a Q there. If it was rational, etc. And so same for if it's, integer valued, etc. Let me do problem number 20. So again, this is just terminology. So r of x is equal to the cube root of 100 plus 2x minus x squared. Since this has a radical, we'll call it a radical function. Since I have a cube root. Let me do problem number 22. F of x equals absolute x minus 5. Well, since it has an absolute value, I'll call it an absolute value function. (24) f of x equals 3x to the 2/3. Okay, so since this is some x to a power, we'll call this a power function. So any function of the form some constant times x to a power is called a power function. And so in this case, it doesn't matter if the exponent is an integer, or in this case, a fraction, a rational number, a real number, or anything. If it's to any power and it's just one term, it's called a power function. You weren't able to get number 20. Oh, okay, so and so the reason we call this a radical function is because we have a cube root. And so since I have a radical, it's called a radical function. And so anything with a radical involved in the um, independent variable, involving the independent variable, is called a radical function. What is a radical? Uh, so th- that's a radical. So this symbol, whenever you have that symbol, that's called a radical. The cube root, square root, fifth root, this is called the radical symbol. So anything involving that is a radical. And so anytime we have this, we'll call it a radical function. Okay? So sometimes, so instead of saying like cube root or fourth root, we also call them radicals. Just another name for it. Let me do, oh, polynomial. Ah, sure. What's the difference between a polynomial and a power function? Well, two things. A power function, it could have this exponent here could be any sort of power. So this exponent could be anything. For a polynomial, it has to be a whole number exponent. And for a power function, it can only be one term. So you can't have, if I wrote 3x to the, you know, 5 thirds plus 4x squared, this would not be a power function. This would be a power function. That would be a power function. But in total, it would not be a power function. And so if you had a polynomial, then this is a polynomial because each of the exponents are whole number exponents, and each of these terms are power functions, but in total, since you've added them, it is a polynomial. Is that clear? And so for a power function, you could have any sort of exponent. You could have 4x to the 7.8. That would be a power function. This would also be a power function. It would also be a polynomial, but that'd be a power function. Okay, so if you only have one term, that's called a power function. 26. Okay, no problem. 26. F of x equals x cubed plus 2 if x is greater than or equal to 3, 3 minus x if x is less than 3. Okay, so in this case, what I notice is that this function actually has two different rules. It has a rule for one part of its domain, and it has a rule for another part of its domain. And so there's some restriction on what the rule is depending on the differing values of your independent variable. And so we call this a piecewise defined function. So in a piecewise defined function, differing rules are associated with differing parts of your function. And so I have differing rules defined for differing pieces. And so it's called a piecewise defined function. So for particular values of your independent variable, you'll have one rule. For other values of your independent variable, you may have a different rule. And so you may have a list of several differing rules for differing values that your independent variable may take. And so if you see this sort of function where it's given as having multiple parts, for rules given for differing pieces of your function, it's a piecewise defined function. Let me do problem number 28. Okay. F of x equals 1 plus or minus rad x. So in problems number 20, let's see what this is. Problems number 27 through 32. Determine whether the complete dependency statement defines a function. And so, if you recall, in order to have a function, you must have that whenever you input a value, you must have a unique output. And so if I give you a input, is the output unique? If it is, if it always is unique, then it is a function. If you can find a case where the output is not unique, then this will not be defined as a function. And so, if I look here, well, if I just looked at the value, I don't know, let's say when x is 1, then it'd be 1 plus or minus the square root of 1, 1 plus or minus 1, but well, 1 plus or minus 1 gives you, well, 1 plus 1 is 2, but then 1 minus 1 is 0. So if you input 1, you actually get two differing values depending on if it's plus or if it's minus. So therefore, this is not a function. Oh, I'm sorry, this was problem 30, by the way. Therefore, this is not a function. Because if I input x, I don't have a unique output. If I looked at problem number, let's say 28, g of x equals 2 minus rad x. Well, if I put in any value for x, then 2 minus the square root of x is always 2 minus the square root of x. And so you always get some sort of unique output. So whatever output you get, if you get an output, it will be unique. Therefore, this is a function. So if you put in some value of x, I don't know, let's say 7, then 2 minus the square root of 7 is 2 minus the square root of 7, always. Why isn't number 30 a function? So notice here that, let's say, let's input 2 or something. It would be 1 plus or minus the square root of 2. And so your answer is, so y is equal to 1 minus the square root of 2, and y is equal to 1 plus the square root of 2. So the problem is well, what is y equal to? You can't tell me. Well, sometimes it's 2, sometimes it's minus 2. So think of this as, you have a vending machine, and you select number 2. Well, sometimes you get 1 minus the square root of 2. Sometimes you get 1 plus the square root of 2. So you select number 2. Sometimes you get a candy bar. Other times you get coal. And so, and you don't know which one you're going to get because it's either minus or plus. Okay. Yeah, it's because of the plus or minus. Hmm. Okay. Let me do problem number 32. G of x equals plus or minus absolute x plus 2. Again, if you input some value, let's say 0, then you get 0 plus 2 is 2. Absolute value of 2 is 2, but it's plus or minus 2. So sometimes you get 2, sometimes you get negative 2. So this is not a function because your output is not unique. And so this is not a function. Okay. So I've given you the idea of a function is some sort of dependency statement. Then I was saying, well, it's some sort of function machine. Now let me give you an idea of a function as being something related to an ordered pair. So an ordered pair. So first, let me tell you what a relation is. A relation R is a set of ordered pairs. And so R is just some sort of set of ordered pairs involving x and y. A function is a particular type of relation. So a function, well, let's say a relation f is called a function if the set of ordered pairs has distinct first coordinates. When written as a set. Okay. And so let me do on page 354, let me do problem number, let's say, 34. And so now what we're going to do is we're going to look and see how to classify ordered pairs to see if they are um, functions or not. In exercises 33 through 40, determine if the table defines a function or not. And so if this set of ordered pairs is a function or not. So x, g of x. Okay. And so 1, 2, 3, 2, 5, 6. 5, 1, 2, 3, 0, 7. And so let's check to see if this is a function or not. Okay, so basically I want to see if there are repeats for the first coordinate. Well, if I look here, notice that if I input 2, then I have different outputs. So this is bad. You select number 2, sometimes you get a 1, sometimes you get a 3. So sometimes you get a candy bar when you put a 2 in, select number 2 in your vending machine. Sometimes you get coal when you select number 2 for your vending machine. So obviously you don't want that. And so notice that sometimes you input 2. This gives you an output of 1. Sometimes you input 2 and you get an output of 3. This is using the rule G. And so using the rule G, sometimes when you input 2, you get an output of 1. Sometimes when you input 2, you get an output of 3. And so no, G is not a function. You want a unique output. So notice that no, this is not a function because in the set of ordered pairs, you have the ordered pair 2, 1, and you have the ordered pair 2, 3. And so therefore, you have the same x coordinate for two differing values in your function. So this is not a function. This is not a function. It's a relation, but this is not a function. So G is a relation, not a function. It's a set of ordered pairs, but it is not a function because for the input 2, you get two differing outputs, 1 or 3. Let me do problem number 40. X P of X 2, 3, 4, 5, 6, 7, 8. Okay, so now if I look here, each of my x's are distinct. Each of my first coordinates are distinct. So therefore, yes, P is a function. Let me do an example. Let's say I have the following. Say this is x, and this is f of x. 1, 2, 3, 4. 1, 2, 5, 4. And so now the question is this a function or not? Well, it turns out that in this case, the answer is yes, it is a function. So notice that in this case, yes, f is a function. The reason for that is we actually have to be a little careful in this case. If I look at the function f as a set of ordered pairs, it's the ordered pair 1, 2, 3, 4, 1, 2, but 1, 2 is, I've already written it down, so I don't repeat it, and 4 and 5, 4. And so, since if I write a set, when I write a set, I do not write duplicates, then um, there is no repeat in the first coordinates. So just because I happen to write this table sort of incorrectly does not mean that, well, it's not really incorrectly. I wrote this table sort of almost to fool you. Uh, and so uh, the 1, 2 is really not repeated. So in this case, this is really not there because I've already written it once. So in this case, each of the x coordinates are different and distinct. And so I have to sort of modify what I said is, yes, they're different. The first coordinates are different and distinct, but you have to get rid of any duplicates because you're writing it as a set. And so that's why I sort of included that additional sort of statement saying uh, in the set. So it's written as a set. Oops. But why a function? It's a function because if I look here, a function is a set of ordered pairs. There it is. It's a set of ordered pairs such that the x coordinates are distinct. Well, let's see. Are 1, 3, and 5 distinct? Are the first coordinates distinct? Yes. 1, 3, and 5 are different numbers. So therefore, yes, it is a set. It is a function. This set of ordered pairs is a function. Is that clear? Okay. Um, now let me do this like a rule. So, oops, or really a set, but I'll say a rule. And so, suppose I have some set here and some set here. And this is some x, and this is some y. And I'll call this rule F, and I'll call these sets x and y. So a rule F from x to y is a function if for x in the set x, there corresponds a unique value y in the set y. So for x in the set x, there is a y in the set y, and this is called the image of x under the mapping under the rule f, and is denoted by y equaling f of x. So notice that for this x, there is a unique y. And so for this x, we have a unique y. Now, we will call this set of images the range of f. I will call the set of all x's which have an image under the mapping f, the domain of f, I will call the y here the codomain of f, and we'll call the x here the co-range of f. Some books have that the co-range is the same as the domain, so they restrict it. But I won't necessarily because I'm lazy. Okay, so let's do some examples. So just remember that for any x, you can only have one y. Let me do problem number 44. So this is on page 354. In exercises 41 through 51, determine whether the rule of correspondence defines a function. And so let's see if this rule defines a function. So let's do 44 first. So I have here, this is x. And there's 1, 2, 3. And then there is here, y. And it's A, B, and C. And so 1 goes to A. That's F. 2 goes to A, C. 3 goes to C. Okay, so now the question is, well, is this a function? And the answer is no, this is not a function. The reason for that is, if I look here, if I input 2, sometimes I get A and sometimes I get C. So it means that, again, if I had this vending machine, so the function machine, and I selected 2 on the vending machine, well, sometimes I'll get uh, A and sometimes I get C. So sometimes I'll get A, uh, I don't know, uh, a candy bar. So sometimes you get a candy bar and C, coal. So if I input 2, if I select 2 on the vending machine, I get a candy bar, or sometimes I'll get coal. And obviously you don't want that. And so notice that in this case, the fact that 2 goes to 2 different things, that's bad. Okay? And so that's the thing that's the error here. Is I look here under my X's, and if I have that they go off to 2 different objects, then this is something that's not allowed. Let's try to find the domain of my relation here. So again, this is some sort of relation. So let's find the domain. Well, in this case, I have that 1, 2, and 3 all have outputs. And so the domain is 1, 2, 3. Let's figure out the range. And so the range is, well, A and C had came from some input. And so A and C are the images of some input. And so the range is AC. Let's find the codomain. Oops. Let's find the codomain. So in this case, well, the range of possible outputs is A, B, and C, even though B is never actually a output for any input. And the co-range the set of all possible inputs are 1, 2, and 3. Okay. So in this case, the domain and co-range are the same, but the range and co-domain in this case are different. And that could certainly happen. Let me do problem number 49. And so PQ RS. So here's my X. And U, V, W. Here's my Y. And so P goes to W. Q goes to U. So this is the rule's called F. W, R goes to W. And, oops, S goes to U. So in this case, again, because I look here at Q, and well, you have an input at Q, but your output is either U or W. And so since Q goes to U and W, then I have that F is not a function. It is a relation, but not a function. Let's find the domain of F. Well, the set of all inputs, P, Q, R, S, the range of F, the set of all outputs, U, W. Let's figure out the codomain. So my codomain is U, V, W. And let's figure out the co-range. The co-range is, well, PQRS. Let me do problem number 53. The cost. C, revenue. R, and profit. P, on X items, is C of X is just 2500 plus 2.5x. Maybe I'll write it here. C of X equals 2500 plus 2.5x. R of X is equal to 8x. And P of X is equal to 5.5x minus 2500. So I should note here that the profit is just the revenue minus the cost. What are the cost, revenue, and profit if the company produces 15,000 items? Okay, so let's do that. So I want to find the cost of 15,000 items. Well, this is given by 2,500 plus 2.5 times 15,000. And so 2.5 times 15,000 is 375,100. So 35,500, which is just 40,000. Let's find the revenue. So the revenue is just 8x. Revenue on 15,000 is 8 times 15,000. Well, 8 times 15,000 is 120,000. So that's the revenue on 15,000 items. And let's find the profit, which is actually revenue minus cost. So I know it's 120,000 minus 40,000 is 80,000. But let's plug this in. So the profit is 5.5x minus 2,500. And so let's multiply 5.5 times 15,000. So that's 65. And so 42,500 minus 2,500 gives you 40,000. Screen is frozen. Oh, okay, so it unfroze for you, I guess. Sorry about that. Okay, so I'll leave it up here for a second then to be sure that you have all this. So to figure out the cost at 15,000, I know that the cost is just 2,500 plus 2.5 times how many items you produce, which is 15,000. So you plug that in, you get 40,000. Wait. One second. Wait 1 second. 5 is 65,000. That's 71. That's wait 1 second. Sorry. Let me just check something here for 1 second. Now that I'm doing this, so that's 75, and that's 75. So that's 82. 500. There was a typo. Sorry about that. That's 82, not 42. Uh, okay, so to find the cost at 15,000 items, I just have, well, I know that the cost for X items is 2,500 plus 2.5 times how many items you sold, which is 15,000. So I plug that in, I get 40,000. The revenue is just 8 times the number of objects you sold, so 8 times 15,000, 120,000. The profit is given by 5.5 times the number of objects you sold, 15,000, minus the 2,500. And so 82,500 minus 2,500 is 80,000, which is good because profit is revenue minus cost. Okay. Before I had it written slightly incorrectly. Okay, so um, let me do problem number 59. The price P per bushel of corn after X months, X number of weeks. After the harvest is given by P of X is 2 plus 0.001x plus, oops, sorry about that, plus 0.01 x minus 0.02 x squared. Should the farmer sell his crop after 2 or 3 weeks? Okay. So let's see. And so let's see if you should wait 2 or 3 weeks after the harvest to sell. He obviously wants to sell it when his price that he can get is higher. And so let's see what the price is after 2 weeks. And so after 2 weeks, it is 2 plus zero point zero 0.01 times the number of weeks minus 0.02 times the square of the number of weeks. And so the price after 2 weeks is 2 plus 0.02. 0.01 times 2 is 0.02. 2 squared is 4. And so my price is 2 plus, 2 plus 0.02 is 2.02 minus 0.02 times 4 is 0.08. And so he can sell it for $1.94. Or whatever units. I'm assuming it's dollars, but let's see after 3 weeks what he can sell it for. Well, it's 2 plus 0.01 times 3 minus 0.02 times 3 squared. And so after 3 weeks, you can sell it for 0.01 times 3 is 0.03. 3 squared is 9. 2 plus 0.03 is 2.03. 2 times 0.02 times 9 is 0.18. Also, he has to sell it for 18 cents less. So that's $1.85. And so after 2 weeks, he can sell it for $1.94. But after 3 weeks, he can only sell it for $1.85. So he should sell after 2 weeks. And in the near future, we'll actually be able to figure out when exactly is the time that he should sell, when he should maximize his price that he gets. And it'll be a relatively easy formula that will be uh, deriving in a few weeks. So let me give you functional notation. Which we've sort of been going through. I've been giving it to you sort of on the sly. So suppose I had y equal x squared. And suppose I ask you to determine the value of y when x is equal to 2. Well, that would be easy. You would just replace x by 2, and so you get y equals 4. Okay, that's fine. Now suppose I ask you determine the value of y when, let's say, x equals 3. Well, again, you would just replace x by 3, and so you get y equals 9. This is all nice and fine, but maybe there is a easier sort of notation that would tell you this. And so, suppose I give you this functional notation, which will just be a shorthand for what we've done above. And so, instead of saying y, well, I give it a name, f. And so, instead of saying y, I'll say f of x is x squared. So instead of saying y equal x squared, I'll give the name of the rule f and the name of the independent variable x. And so if I wanted to say determine the value of y, of f, when x is equal to 2, that's all I would need to write. And so this whole phrase, determine the value of y when x equals 2, is written in this shorthand functional notation. And, well, the way we would find it is exactly the same way we did above to figure out f at 2. Wherever I see a 2, wherever I see an x in the function, I replace x by 2 and evaluate. Similarly, if I wanted to figure out the value of y when x is 3, I would just replace x by 3 and evaluate, just like what we did above. So note let's say f of 3. So this is read as f of 3. And so this is what when I write this, you say whatever the name of the rule is, of, and then the wherever you're evaluating. So f of 3. And this means to evaluate f, the rule f, when, well, at the value 3. Okay? So let's do some, oh darn. I guess let's do some examples tomorrow. It's already 12:45. Actually, it's 12:46 right now. So I guess I will do some further examples. Well, I'll do examples. I haven't done any examples yet of functional notation tomorrow. So I'll finish off this chapter tomorrow. And I guess I'll see you then, unless there are any questions. Okay. So I'll see you tomorrow.